Hey guys, so obviously this is super less than ideal, but I would rather do our lecture notes this way than us get behind at the literal beginning of the year. Super annoying. So I'm going to go ahead and minimize my face, and we are going to talk a little bit about some biochemistry. Hopefully yesterday you saw a little bit of the context as to why we have to talk about biochemistry in this class, or chemistry in general in this class, and it's because we as organisms are made up of these chemicals, so we have to understand a little bit how they work together to figure out how to build a organic or living creature. So I'm just going to kind of go through what I wanted to talk about today anyways, and at the very end of this I'll put a slide up that will be the notes that I would have taken on the board with you guys today. So starting off, luckily there's a bunch of this stuff that we're going to be able to skip because you guys remember it from physical science class. So we are going to skip elements and matter and atoms and all of that. Now, just to sit on elements for a second, so periodic table's got like 100 and some odd elements on it, and most of those honestly don't matter. A lot of the ones towards the bottom are kind of made up anyways, in that they are not found in nature and you can only get them in a lab. These are the elements that we super care about: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those are the ones that make up almost entirely your body. Specifically carbon, hydrogen, and oxygen, they make up like 96% of all of the matter within you. Carbon is what we call organic. It's the base for organic chemistry. It's the base for organic life. And we will talk a little bit about that probably some point. I'm not sure. We're not doing it today, so probably sometime next week. But yes, so these are overwhelmingly what we are made of. We're going to skip through atoms and electrons and things. And we'll go here. Let me move my face out of the way a little bit. Up here. Alright, so I want to talk about some different types of bonds, chemical bonds, and ways that atoms interact with each other, because it is relevant for our class. So first of all, I want to talk about covalent bonds. Hopefully you can, have this rattling around in the back of your head from whenever you took physical science, but a covalent bond is how you make a molecule. So it's actually the strongest type of chemical bond, and it is because it is the sharing of electrons. So if we see here, we have this nitrogen atom right here, and these bars are representing that they are sharing electrons with all of these hydrogens. Now, the nitrogen is really strong, and it is going to hold tight to those hydrogens' electrons, and so it's really, really hard to tear that molecule apart because the nitrogen really wants the electrons that the hydrogen has. It's not strong enough to straight up take those electrons away, so it is going to instead share. Sorry, I have my notes on this screen over here. Sorry if it's weird. So in our class, we're going to be talking about molecules a lot, and molecules are always held together with covalent bonds. There are a couple of different types of covalent bonds. There are polar covalent and non-polar covalent bonds. And we kind of tend to drop off the covalent bond portion of this and just refer to molecules as being polar or non-polar. So when I say polar, you probably think, and that's why I have a picture of Earth over here, you probably think like cold, right? Because on Earth, the North and South poles are really cold. Well, they're not called the poles because they're cold. They're called the poles because they are the opposite ends. So think about like bipolar. You have like this mood and this mood, and it swings way back and forth. So when something is polar, it just means that there is a this side and a that side. So we would call this particular covalently bonded molecule polar, because this nitrogen's really beefy, and it is going to pull really hard on those hydrogen atoms, or the electrons that are in these hydrogen atoms. Now, again, it's not strong enough to completely steal, but it is strong enough that, like, it's going to get the majority of the custody of those electrons. So, the molecule itself is not got a charge to it. However, if you look at the individual atoms, the nitrogen is going to be holding those electrons closer, so it has a slight negative charge. And that's what you can see with these arrows here. They're saying that these electrons are kind of shifting closer to that nitrogen atom in the middle there. So this would be a polar covalent molecule in that it has a slight negative area up here with this nitrogen and all its electrons, and then it has some slight positive areas down here with these hydrogen atoms. Whoops, go back. Now, this guy down here is a non-polar covalently bonded molecule because the fluorine and the boron are all pretty equal in beefiness, and so these fluorines are actually going to pull a little bit harder than the boron even because just he's only pulling against 1, he's pulling against 3. So you're getting kind of an equal tug of war in every direction, and so there is no one area of this molecule that has more electrons than another. So overall the molecule has no charge, and then individually the molecule has no charge. The atoms within that molecule have no charge. So we would call that a non-polar covalently bonded molecule. Moving on. So we have our covalent molecules, which are covalently bonded molecules, which are sharing electrons amongst all of the atoms. Then we have our ionic bonds, which are the stealing of electrons. So here we have this magnesium, and it's got some chlorines that are kind of buzzing around here. And this magnesium really does not like having 2 random electrons in this outer, what we call the valence electron shell. It wants to have this full of electrons, and it doesn't, and it's got a long way to go. It would actually much rather lose these so that we shift down into the next layer, and that layer is full. Now, chlorine, on the other hand, only needs 1 more to be full up, and so chlorine is going to aggressively steal that electron from this magnesium. So what we end up with is a chlorine with an extra electron, electrons being negatively charged, gives this chlorine atom a negative overall charge. Now, this magnesium has lost 1, 2 electrons to 1, 2 chlorines, which means that he has -2 electrons. -2 negatives is a +2. So this magnesium atom now has a +2 charge. Now, because the atoms themselves have charges, they're going to kind of stick together like magnets a little bit. An ionic bond is quite strong when it is dry, but when you get this thing wet, it falls apart really easily. A lot of times we would refer to these as ions or salts or electrolytes. So that's why I have a picture of Gatorade here. Gatorade is literally just, we took some of these ionically bonded ionically bonded compounds and dissolved them in water and then put blue food coloring in it. Now, the reason that you drink this is because your nervous system actually runs on electricity, and you need these ions to maintain that electric charge within your neurons. And so whenever you sweat and lose a lot of salts, sometimes you get really crampy because you're not able to shock your muscles the way that you need to get them moving. And so you drink salts in the form of electrolytes to help rebalance the salts within your body. All right, anything else I wanted to say about that? No. Okay. So the final bond that I want to talk about, maybe you guys talked about this in physical science. I don't know though. This is what is called an intermolecular bond, because it's not one atom to another, it's actually one molecule to another. And these are hydrogen bonds. So here we have water, which is the most common compound molecule, that does these hydrogen bonds. So water is made up of polar covalent bonds. We have this oxygen, which is the big red boy back here, and we have these hydrogens, which are the little gray ones. This oxygen is super big and super beefy, and he is very electronegative, which means that he is going to pull those electrons really close. They're still sharing, but he's going to pull them closer. It's like he gets full custody of the electrons, and hydrogen can only see them on the weekends. So those hydrogens, because they are farther away from those electrons, are going to have a slight positive charge, which is what we can see here. This little symbol, this like weird, looks like you messed up drawn an S, it means partial. So we can see here, this is a partial positive charge to this overall neutral molecule. Now, this oxygen is pulling those electrons closer to it, which means that the oxygen has a partial negative charge. So water molecules, the molecule itself kind of works like a little magnet, in that if you put a bunch of water molecules together, the positive ends on the hydrogen sides and the negative ends on the oxygen sides of two different molecules will start to have a slight attraction to each other. And these are called hydrogen bonds. And we will talk a lot more about these later, because hydrogen bonds are what give water all of the really cool properties that you guys probably have talked about, like adhesion and cohesion and surface tension and evaporative cooling, and we'll talk about all of those again. So last thing I promise, let me make sure how I'm doing on time. Sure, that's fine. All right, last thing I promise. I want to just remember real quick, or remind you guys real quick about some of the language that we talk about chemical reactions. So here we have a chemical reaction. We have methane, CH4, I believe that's methane, and we are mixing it with oxygen. Usually you would be burning this. That's why this is what would be driving this reaction forward. And you would get CO2 and water, and this is your typical combustion reaction. Oops, my computer did a weird thing. Alright, anyways, my bad. Picking back up. So this is your usual combustion reaction. It's what happens when you burn stuff. So these things on the left we would call the reactants, because they are going to react with each other. The stuff on the right here we would call the products. This is an arrow that means yield. We don't usually use equal signs when we do chemical reactions because they can go back and forth. So we have, again, our reactants yield our products. And what I really want to focus on here is, one, conservation of mass. We're not losing anything. We have this one carbon, this black bubble, and we have a one carbon here. We have 1, 2, 3, 4 oxygens, 1, 2, 3, 4, and we have 1, 2, 3, 4 hydrogens, 1, 2, 3, 4. So the law of conservation of mass says matter can neither be created nor destroyed, only transferred or transformed. And so that is what we're doing here. Nothing is going away. We're not getting anything new. We're just kind of breaking it up and reassembling it into new bits. Now this next part has to deal with the energy that goes into these chemical reactions. So I kind of like to think of it as Legos. Okay, if I have a pile of Legos on my table, it is not just going to magically become something. I'm going to have to use energy and probably time to build and snap them all together. So whenever you build a molecule, you are using energy, which means that you can basically take all of the energy that you've put into this molecule and it will be stored as potential energy. It's kind of like when you push a ball up a hill, all of that potential energy or all of your kinetic energy of pushing it is going to be stored as potential energy, and then when you release it, it will roll, releasing that potential energy back into kinetic. So it's the same thing here. You're taking all of that potential energy, or all of the kinetic energy of you building this, and storing it as potential energy within the bonds. Now, when you break a molecule, it's kind of like a tiny explosion. It releases all of that energy back out into the environment. So again, we have our products here. Now we have our reactants here. We're going to use energy. We're going to use the energy of them breaking to rearrange them and store that energy as the reactants. So I'm going to get rid of my face. There we go, hopefully. And these are the notes that we took today. They are all in Google Classroom in the notes document, I believe. And please email me if you guys have any questions. And again, I'm really sorry that it's like this, but sometimes you just must persevere. Okay, goodbye.